Hi everybody. It's about to get dangerous, so we're wearing our helmet. Why is it getting dangerous? Because we're getting into Lewis acids and bases, and there's a lot of donation of electrons that go on in this piece. We can see here a pretty darn tootin' meme of Lewis base swearing fealty to the Lewis acid by donating its electron pair to that Lewis acid. As you have probably learned in definitions of acids and bases, Lewis acids and bases are defined by electron donation or electron acception. So let's get into it. Lewis acid-base theory focuses on the transferring of an electron pair. The lone pair on a generally electronegative atom attacks a relatively electropositive ion. Attack is dangerous! It does not necessarily require H atoms. You'll learn a lot more about that in organic chemistry. The electron donor is called the Lewis base. It is electron-rich, electronegative. Therefore, it is a nucleophile. It is a friend of the nucleus. Why is it a friend of the nucleus? Because something that is electron-rich has a partial negative charge. That partial negative charge is attracted to the nucleus of another atom, which has a positive charge. Negative attracted to positive. Makes sense. The lover of nuclei is attracted to positive charge. Our Lewis base must have a lone pair. The electron acceptor, the thing that is getting that lone pair donated to it in theory, is called the Lewis acid. That is an electron deficient molecule or atom, and therefore it is an electrophile. It lacks electrons because it doesn't have enough of them. It has a partial positive charge. Lover of electrons, attracted to negative charge. So, let's keep going. So, in our Bronsted-Lowry model, we focus on the proton, the H+. In the Arrhenius model, our base must be an OH-. In the Bronsted-Lowry model, our base can just be anything that accepts a proton. In our Lewis acid-base theory, we're talking about electrons. So, NH3 is the Lewis base. We have an electronegative N, which, if we remember our electron geometries and whatnot, this is trigonal pyramidal, and the N has a partial negative charge in a polar molecule. That lone pair is kind of the locus of that negative charge, that partial negative charge. That lone pair will be attracted to our proton, our H+, and perform a nucleophilic attack, bonding to the H+ and forming NH4+. I have rewritten this NH4 in a certain way so that we can see the lone pair is now part of a single bond between the H that we attacked and the NH3 that donated. Lewis acids are electron deficient. So here's a little bit about their strength. Either it's electropositive because it's attached to an electronegative molecule. For instance, we have H's in water, have a partial positive charge. That makes them a good site for the attack of a Lewis base. So the more electropositive the atoms, the stronger the Lewis acids. So for instance, an iron ion, Fe3+, is very positive. Therefore, it is a good Lewis acid because it has a lot of positive charge. A H on a water molecule is still positive. It can still be a Lewis acid, as we know from water's electropositive, from its acid behavior, going from H2O to OH-, donating a proton, but we can also think of it as accepting electrons, the H. Boron is another very electropositive atom in typical molecules. They must have an empty orbital willing to accept the electron pair. So H plus has an empty 1s orbital, and the B in BF3 has an empty 2p orbital to accommodate that lone pair. The strength of the Lewis acid also depends on atoms bonded to the central atom. The more electronegative the periphery atoms bonded to an electropositive central atom, the stronger the Lewis acid. So BF3 has 3 very electronegative fluorines attached to it. That makes it a better Lewis acid than any boron-oxygen type compound would make boron. BF3 is a stronger Lewis acid than BCl3 because Cl is less electronegative than F, and so it's less electron withdrawing from that boron atom, and so BCl3 is weaker as a Lewis acid than BF3 is as a Lewis acid. And we say that in that blue language right there. Blue, kind of like my awesome shirt. See them flowers? Woo! Lewis bases, conversely, are things that have lone pairs, and they are willing to give those electrons to other atoms. Must have a lone pair to donate to our Lewis acid. Anions are better Lewis bases than neutral atoms or molecules. So for instance, N- is better than N in any compound. Generally, the more electronegative an atom, the less willing it is to be a Lewis base. So sulfur is a better Lewis base than oxygen because sulfur is more willing to get rid of its electrons than oxygen is. Oxygen is greedy. It's very electronegative. Therefore, it holds onto its electrons tighter and is less willing to donate them. The strength of a Lewis base also depends on atoms bonded to a central atom. The less electronegative the atom bonded to a central atom with a lone pair, the stronger the Lewis base. So for instance, if we look at NF3 versus NH3, N can serve as a Lewis base in both types of molecules because it has a lone pair and it's relatively electronegative. But the NH3 is a better Lewis base than the NF3 because the F is pulling some of that electron density off of the N in NF3 and thus weakening the ability of N to donate those electrons to a Lewis acid. So let's do an example. What's the strongest Lewis acid that we see here? Pause the video, make a decision, and then we'll get the answer when we come back. Okay, now that you have thought about it, let's look at the answer. That is AlF3. Why? Because aluminum is very electropositive and it has more electronegative atoms attached to it. BF3 and B and Al are in the same group of the periodic table, but because B is a smaller atom with less electrons, it has a harder, it's smaller, it's less electropositive than aluminum is. And then the Cl, the F, the Br is just rating the different levels of electronegativity of the surrounding atoms, and F wins that battle. So AlF3 is the strongest Lewis acid of these. Let's do the base. Ready? Pause. Okay, now that you have made your decision, let's look at this. Which is the strongest Lewis base? Well, the answer is OH-. 1. It's a negative ion, so it has excess electrons to donate. 2. It's not attached to fluorine, so the H is more electropositive than the fluorine is. Therefore, the O in OH- is better able to donate its electrons to a Lewis acid. Now, let's talk about Lewis acid-base reactions. The base donates a pair of electrons to the acid. It generally results in a covalent bond forming. So, if we have NH3 acting as the Lewis base with BF3's Lewis acid, you see that the lone pair has essentially become a bond to the BF3. The product that forms is known as the adduct. So the H3NBF3 that we see on the products is the adduct. Arrhenius and Bronsted-Lowry acid-base reactions are also Lewis acid-base reactions. It's just the Lewis is a bigger umbrella than the Bronsted-Lowry and the Arrhenius. Here's a few more examples of our Lewis acid-base reactions, and we can see the arrows dictate how the electrons donate and move around in this reaction. So our Lewis base that we see there, which is a dimethyl oxygen compound, is going to donate the electrons to the H, which liberates it from the Cl-, and our O plus CH3CH3H molecule is now the adduct, and the Cl- just floats off. But remember, HCl is a strong acid, so in all likelihood, the H3O plus is already floating around without the Cl- in this situation. Here's another one. We see again the reaction between ammonia and boron trifluoride, and it forms the adduct that we see there. We have a few more examples. In this first top reaction, this carbon, because it's attached to an oxygen, is relatively electropositive because of the polar carbon-oxygen bond. Again, the Lewis base donates its electrons to the carbon, forming this adduct. And we see because the carbon can only have the octet rule, the oxygen just basically accepts one of the bonds as a lone pair. You can also have the reaction of metal complexes to form Lewis acids and bases. So here we see a lone pair from two ammonias are donated to a silver, forming an adduct where the silver is complexed with two Lewis bases, NH3s, as the adduct. So let's look at this reaction. Identify the Lewis acid in the forward reaction. Ready? Pause. Okay, now that you have figured out what the Lewis acid is, let's find out the true answer. It is the Au3+, because remember, a Lewis acid is very electropositive. What could be more positive than 3+? You ask me. I don't know. Actually, a 4+ would be more electropositive than a 3+. We could keep going forever. What's the adduct? It's HAuCl4. Why? Because the Au is being attacked by Cl-, and that is forming the adduct of HAuCl4. Now let's look at this bad boy. Here we see a complex ion, that's what this is called right here, with its counter ions. And my question to you is, which one of these guys is acting as the Lewis base? This is essentially our adduct that is the end result of the Lewis acid-base reaction. Ready? Go! The answer, of course, is NH3, because we can see the NH3s have interacted with our small cobalt positively charged ion. The Cl-, we must remember, are there just to balance out the 3+ charge on the overall thing. But the NH3s are what have actually attacked our positive metal ion and formed this complex ion. So NH3 is the Lewis base, and this right here is our adduct. Okay? Roger Dodger. That's it.